Hello and welcome. In this video, I'll be covering section 5.1, which is over inverse functions. My goal for you by the end of the video is to be able to determine whether a function is one-to-one, and if it is, find a formula for its inverse, and then simplify expressions of the type f of f inverse of x as well as f inverse of f of x. So we'll go ahead and start with talking about inverses as well as one-to-one functions. So a one-to-one function is essentially a function such that when you have two different inputs, you never will get the same output, meaning every x is paired with exactly one unique y, and every y is paired with exactly one unique x. So basically, I can never have two different numbers that when I plug in give me the same y value. Different way of saying that is if you have two outputs that are the same, then that means that the two inputs cannot be the same. When a function happens to be one-to-one, then we actually can say that its inverse, or f inverse, as this is being notated. Notice the -1, what looks like a -1 exponent. But again, this is read right here as f inverse. If it happens to be, or if the original function f is one-to-one, then its inverse will also be a function. And some things that are important about how functions and their inverses relate to one another is the domain of a one-to-one function will always be the range of the inverse function, just like the range of the original one-to-one function will also equal the domain. So basically the range and domain perfectly swap when you compare the original function with its inverse function. Now, a function that happens to be always increasing or always decreasing is guaranteed to always be a one-to-one function, and that's going to be what we'll take advantage of, that last statement, that if we know it's always coming up the page or always going down the page on the entire domain, so for the entire graph, at that point you can conclude that it would be a one-to-one function, which then means its inverse also would be a function. So it's really that last statement that we're going to take advantage of here for these types of questions, where it will say, here's your function, f of x, in this case equaling 2x minus 3, prove that it happens to be one-to-one. Well, based on what we know about this function, it's linear, so if I were to maybe sketch this, I know it would cross down at like -3 and have a positive slope. And if we were to think in terms of, well, is that ever going to switch from increasing to decreasing? Well, since it's linear, it's either always going to increase or always going to decrease. So this one, since it does always increase, it's always increasing. That then means that it's one-to-one. Which then our conclusion that we could make, since that is one-to-one, is if I were to find the inverse function also would be a function. Let's go ahead and try another one. This one's giving us a g function, so g of x in this case is x squared. So once again, we could think in terms of, what do I know about this graph? That should be one of our original parent graphs that we know, which is the parabola centered at the, or with a vertex at the origin. If we think in terms of, okay, is this going to be one-to-one? Well, we could look at this and go, well, I guess it's technically decreasing over here, but now it's actually increasing over here. That's doing both. So since this increases and decreases, we can then say it's not one-to-one. Because again, to be one-to-one, it has to be either always increasing or always decreasing. If you even have one interval that's doing the opposite of another interval, meaning if one's decreasing but you notice there's another one that's increasing, at that point in time you can go ahead and say, nope, this one is not one-to-one, so the inverse would not be a function for this particular expression. Now let's go ahead and kind of intro into some of the inverse or finding of the inverses. We'll start with just dealing with coordinate points, or what most commonly is going to be an x comma y. But an inverse relation is something basically where the first and second coordinates that you're given, we just end up interchanging them or swapping them. So that has to do with, back from earlier, that the domain of the original function will match the range of the inverse function. So for this particular example, if it says g is this list of 3 ordered pairs, the inverse function or G inverse, would be equal to the set of points where my x's and y's just swap. So 2, 4 is now going to be 4, 2. -1, 3 is now going to be 3, -1. And the last one, -2, 0, would turn into 0, -2. And all that curly bracket represents is just the fact that this is a set of points. So if it had it to start, we just make sure that we include it with our final answer. So this would be what the inverse for the list of, I guess, those 3 points, or for that G function. This is what that inverse would be. So notice, really all we're doing is just swapping the x's and y's and writing down the new ordered pair. Now when it comes to graphs, one way that we can actually do a test for a one-to-one, not only could we just look to see if it's always increasing or always decreasing, we can actually do a really quick and easy test, which is called the horizontal line test. So remember, we had a vertical line test that told us whether the graph we're currently looking at is a function. What a horizontal line test will do is essentially tell us if the inverse function, without actually seeing it, would be a function. So how this works is if a horizontal line would ever cross over the graph more than one time, so if we go back to maybe the x squared example, where again that was the parabola centered or with a vertex at the origin, if we were to draw a horizontal line, notice it intersects it twice, which then means there's 2 different x's that give us the same y, which goes against what one-to-one really means. So this is just a quick, easy, just like the vertical line test was, a horizontal line test should be just as fast, and all that really is going to tell us is whether that function happens to be one-to-one. If it's not one-to-one, then its inverse would not be a function. Another thing graphically that would be true about inverses is if I were to have 2 functions, let's say I had f and f inverse that truly both were functions, the inverse is always going to be what looks like a reflection over the line y equals x. So if you think in terms of what would y equals x really look like, well, it's got a y-intercept at 0 and then a slope of 1. So essentially it would just be this dotted line that goes through the first and third quadrants. So if I had, say, maybe some graph that looked like this on the left side, the inverse function would just be a mirror image. So it would look something like that on the other side. So if this was f, this would be what the inverse function looks like for that f. So what really you could also do is if you had a t-chart, you could just take the x's and y's, swap them, plot the new points, and then just connect them. Just in your head picture it's going to be a mirror image over this line, and if there's ever any points that lie on the line itself, it would actually just pass through that point specifically, or that would be like their point of intersection. So let's just do a quick few examples here of being able to apply that horizontal line test, as well as maybe picturing what the inverse function would look like. So each of these is just saying, is this one-to-one, and therefore its inverse would be a function. Well, let's look at each one of these individually. The first one, if I were to think of a horizontal line going through this graph, it doesn't seem like there's ever a time where that horizontal line would cross it more than one time. So this one would be a yes, it's one-to-one. And what we would actually be able to do for the graph is just think in terms of if I were to reflect that over that diagonal line y equals x, what would it look like? Well, it actually would retrace itself in this case, because if we took this point right here, which is 4, 0, and swapped it and get 0, 4, notice that point also happened to be on that line. So this one was, since it was perfectly perpendicular to that y equals x line, it actually would be an inverse of itself. If we go to letter B here, if I were to draw a horizontal line, notice it crosses twice, so this one would be a not one-to-one, which then means the inverse function, or the inverse would not be a function. Sorry. If we go to C, looks like this should pass the horizontal line test. I can't see any places where a horizontal line would ever cross it more than once. So this one is a yes, it's one-to-one. I'm just going to start writing one-to-one. And let's see, if I were to try and picture what would the graph of this look like, well, I could kind of take these key points here and just swap the x's and y's. So if that's just a little bit more than 4, that would be 0, maybe 4.1. So then maybe 4.1, 0 would have to be on the inverse function. If we maybe take this point right here, looks like that's at -2, 3. So if I switch that, that would become 3, -2. And let's see if I can take maybe this point right here that's right above 5. It looks like it's -5 and maybe 1.5. So if I went to 1.5 down to -5, it gets me right here. So it seems to me that the graph of this one is going to look something like this. And then notice again the point that actually is on that line will be essentially that point of intersection. So notice without having to actually figure out what the inverse was of that, I didn't even know what the original function was, I was still able to do a rough sketch of what that would actually look like. And then the last one here, D, if I were to draw a bunch of different horizontal lines, it crosses multiple times. And all it had to do was fail it one time. Technically I failed all 3 times that I just drew those, so this one would also be one that would be not a one-to-one function. I don't know why I didn't just write 1-to-1. Well, let's go ahead and move on to this next one. If I were to ask, is this group of points 1-to-1? Notice technically this one is not 1-to-1 because there's 2 of them that would fail the horizontal line test there, and then there's a couple actually on the x-axis that would also fail. So this one technically is not a 1-to-1 relation. However, we still could find the inverse. It just would not be an inverse function. It would just be what we would call an inverse relation. So each of these, again, we've kind of practiced this already. It would just be take the x's and y's and swap them. So 2, 3 would turn into 3, 2. 1, 2 would turn into 2, 1. 0, 0 would remain 0, 0. -4, 0 would turn into 0, -4 down here. -2, -2 also, swapping those, would stay the same. And then the -3, 2 would become a +2, -3. So each of those, if we were to actually draw that kind of diagonal line through each of these, notice the 2 points that actually fell on that y = x line stayed exactly where they were. All the other ones jumped to the opposite side of it. Again, if I were to do that, the grids are a little bit off. But hopefully you can kind of see like the distance away from that for the 2, 3 is the exact same distance as it would be for the 3, 2 away from that y = x, hence why it's a reflection or a mirror image across that line. Alright, let's go ahead and amp things up just a little bit. Now we're actually, instead of just talking about points and graphs, we'll talk about how we actually algebraically find an inverse. First thing we would still want to do is just verify that the original function that they have is 1-to-1. So again, I would want to either think in terms of is it always increasing or always decreasing, or if you can picture what the graph looks like, utilize the horizontal line test. But as soon as I've established, okay, yes, the function f is 1-to-1, what I would then do is go ahead and just replace that f of x or that function notation with y if it didn't already have y there, interchange or swap. So again, interchange is just a fancy way of saying swap the 2 x and y's, or there could technically be multiple x's. So basically every place you see x, put the letter y, and everywhere you see a y, put the letter x. All other numbers and powers and radicals and fractions, all those things stay exactly where they are. It's just the letters that are changing. At that point, you do everything in your power to try and isolate the y, so you would try and solve for y, and then once you have the y all by its lonesome, you then would replace it with the function notation for an inverse. So again, the only way that I can use this, keep in mind this is function notation, it does guarantee for this scenario that the original f function did have to be 1-to-1 in order for me to be able to use that notation. If it wasn't 1-to-1, then we would just keep it as a y, and we would not call it a function, it would just be now an inverse relation. So let's go ahead and try an example out here. Notice this one gives us a function equaling 2x minus 3. We established earlier in this video that that was an always increasing function, which then means yes, it was 1-to-1. So since it is 1-to-1, I can go ahead and find the inverse function for this. First thing I would do is go ahead and replace the f of x with the letter y. Alright, that step was done. Now I take the x and the y and just swap them. So I'm going to write x where y was, keep 2 where it was at, but then switch x now to a y, and then keep the minus 3. Our next step is to then just try and solve for y, so try and get y by itself again. So I would add 3 first. That would give me x plus 3 equaling 2y, and then divide by the 2. And at that point I would be able to say that y is equal to x plus 3 all over 2. If I wanted to split that into two fractions, we could. We could say it's x over 2 and then plus a 3 over 2. But I'm okay with you just leaving it as is. But again, the very last step is, because the original one was 1-to-1, I can use this function notation that they said and rewrite this as the inverse of f is equal to that x plus 3 over 2. And there would be my final result for the inverse of that function f. So notice this one now is just, let's look at what the graphs actually would look like for each of these things. So the first one here, just graphing 2x minus 3, that would have a y-intercept down here at negative 3 with a slope of 2. So I'd do a rise of 2, a run of 1, over and over and over until I run out of grid. And it looks like I should be able to do 1 going down and to the left. So my inverse function, or sorry, not my inverse, but the f function for this one was that line. If I were to now graph the other one, this one is one that I could rewrite technically as an x over 2, or 1/2 x, and then plus 3/2. So I could think of that as slope-intercept form. So I could go to 3/2, or 1.5, and then just perform a slope of 1/2. So I could go up 1 over 1, or sorry, not over 1, but over 2, and then up 1 over 2 again, and then down 1 to the left 2 for the remaining that way, and go ahead and connect those dots. Notice what's happened is essentially it is a reflection over this diagonal line at y equals x, and whatever points lie on that should technically, if I were to draw that a little bit more accurate, that should be their point of intersection, because after all, if it's going through 3, 3, when I swap 3, 3, it's still going to stay 3, 3. So all of the points that are on this y equals x have the exact same x and y coordinates, hence the equation. And thus, anytime you have an inverse graphed with its original, they should, if they ever cross that line, have a point of intersection at that point. Notice the red graph was 1-to-1, and if we look at the blue graph, it is truly a function because, well, it now passes the vertical line test. And I could even look at it the other way. If I said that the blue one was the f, then the red one would have been the inverse. But technically with this one, the blue one was the f inverse, and the red one was really f. Alright, moving on to the next one. This one's a cubic function, which we haven't graphed a whole lot of, but it is one of those parent graphs. This is the cubic function that's been shifted up 2 because there's addition outside, so I know it would have a y-intercept there at 2, and then from there what it would do is go up 1 over 1. So it would have been basically up 1 over 1 because it goes through 1, 1 and -1, -1. Originally, if I just shift those 2 points up 2 places as well, I get these 3. The next point would have been 2, 8, so if I take that point and shift it up 2 places, now it would be at 2, 10. And the other key point on the parent graph would have been -2, -8, but again, shift that up 2, now it would be -2, -6. So the graph of this function is one that comes up, kind of curves a little bit in the middle, and then goes back to going really steep. So if I asked, is this 1-to-1? Try the horizontal line test. It looks like there would be no places where a horizontal line would ever cross more than once. So I would say yes, this is a 1-to-1 function. If it is, it says to go ahead and find a formula for its inverse. So that means I'm going to first replace the g of x with a y. I'll now swap the x and y. So this will now say x equals y cubed plus 2. Notice again the power and the 2 stayed exactly where they were, and now I'll go ahead and try all of the steps to get that y by itself. So I've got x take away 2 on the left side equaling y cubed. To cancel a power of 3, I would introduce a cube root, or a root with an index of 3. So this particular thing solved for y would just be the cube root of x minus 2. And since it was 1-to-1, I actually should be able to write this in function notation and really say, instead of having it as y equaling the cube root of x minus 2, I could say that it's really g inverse of x equals that cube root of x minus 2. The last part of this says to go ahead and graph its inverse. This is not necessarily a common function for us to know, so what we could do is just take some of the points that we plotted and swap the x's and y's. So the 0, 2 that we had would turn into 2, 0. What looks like is at 1, 3 will now be at 3, 1. What's at -1, +1 would now be at +1, -1. What's at -2, -6 will now be at -6, -2. And what's up here at 2, 10 will be over here at 10, 2. So now notice if I were to picture that diagonal line, or that y equals x line right here, that has a slope of 1 and goes through the origin, and just picture a mirror image across that, hopefully it would seem reasonable that it's going to look something like that. And notice again, even though I didn't necessarily know exactly how to maybe graph a cube root function, this is what a cube root function really would look like, I was able to take the original function that maybe we did know the points for, swap the x's and y's, and that allowed me to actually make a nice graph. And notice once again, where they met right here happens to be one of the points that's on that y equals x line. Now some other things that we can do with inverse functions, or some other ways that maybe questions can be asked that involve inverse functions, is if I just give you two random things and just said, are these inverses of one another? One way you could approach it is to just pick one, swap the x's and y's, solve for y, and then compare and just see if it turned into what the other function was. Or what might be a little bit more efficient is to do the two possible compositions that we have. So remember this open O symbol that we have right here meant compose or composition. And what that really means is I'm plugging the f function into the inverse of f function. So again, f would go into f inverse, and what's supposed to happen is it's supposed to just simplify down and leave just the letter x. So if it works that direction, we still have to test the other composition of, well, let's say that that first one, f going into f inverse, turned into x. Let's test the other way. What if f inverse is going into f? Well, notice that also is supposed to turn into x. If that happens both times, because remember the order in which we compose does matter. It doesn't turn into the exact same thing, at least not guaranteed. But if they're truly inverses, the results of both compositions will turn into x. Once you justify that, then at that point you can go ahead and say, yes, those two things happen to truly be inverse functions of one another. So let's go ahead and see this in action here. The first one I'm going to do is the f inverse of f. So essentially that means this 5x plus 8 is going to get plugged in where I see the x in the inverse function. So that would look like 5x plus 8 and then minus 8 all over 5. So notice I just saw where the x was here, and technically I substituted the 5x plus 8 in that position. Now those parentheses I just added to it are completely unnecessary because there's no number in front, so I really can look at this and just go, well, I see that 8 minus 8 is on top, so that would cancel out. That would then turn into 5x over 5. And hopefully at this point you would see that 5 divided by 5 would also cancel, and we could say, hey, that did actually reduce to x. So first check, seems like this is working out. Now we do the other composition, f of f inverse, just to verify, and if this happens to turn into x as well, then we can say, yes, those two truly are inverses of one another. So in this scenario, plugging the inverse function in where I see x in the f function, so that's going to be going right here, so it's going to be 5 times, I'll replace it, so I've got x minus 8 over 5, and then I still have the plus 8 outside. Well, if I look at what happens here, notice that the 5 divided by 5 will reduce each other down, so I'm left with x minus 8 plus 8. Well, x minus 8 plus 8, the minus 8 plus 8 should cancel, and that should just leave x. So since this one turned into x and the first one turned into x, I can now say, yes, for f inverse is truly an inverse of f. So So oftentimes they won't actually use this f inverse notation. Sometimes they'll just say, here's a function f and another function g. Are f and g truly inverses of one another? This one with kind of the notation where they both used the same, I guess, root name of f, kind of was a little misleading here. It kind of almost guaranteed right from the beginning, if that's the notation they were going to go with, that yes, that truly does happen to simplify down to x's, but basically this one just wanted to have us show that that was true, and the fact that those two compositions turned into x is really, all of that work was really to show that, so it's almost more like a proof more than anything. Now the last thought we'll have on this before we kind of close up this section is the idea of what if a function was not one-to-one? Is there a way maybe I could still find an inverse that still would be a function? The way that we would do that is actually restrict the domain of whichever the function is that is not one-to-one and force it to where it would now be one-to-one. So in this scenario, notice again, if it's inverse would not be a function, that means the original one must not have been one-to-one. What we could do is just look at the original, restrict it to where it passes, and that would then guarantee that the inverse actually would now be a function. So a common example that almost always gets brought up with this concept is the parabola, because again we hopefully know that a parabola, if I were to sketch it, is going to fail that horizontal line test, meaning it's not one-to-one. Or you could also look at it and go, well, it's decreasing part of the time but then increasing the other part of the time. It's supposed to be always doing only one of those things, so this is not a one-to-one. What we could do though that would force it to become one-to-one would be to just basically cut off the entire left side and just say I only want the function from its vertex and then to the right. At that point now it would pass that horizontal line test. So if I just said, you know what, let's just restrict this domain to be everything from 0 to infinity, that now is going to make it such that if I did the whole swap the x's and y's and solve, then I should be able to actually say that that is truly a function. I'll just need to kind of note that the domain of this and the range, well, the range of this is from -2 now to infinity. That for the inverse function, if I were to say if that's f of x, the f inverse, forgot my little negative sign here, so f inverse of x, it's going to have a domain that should match the range of what I just said. So the domain of this is going to be from -2 to infinity, and the range now is going to be from 0 to infinity. So notice again, what was the domain now has turned into the range. What was the range now has turned into the domain. And if we went through and actually did the steps, so first thing it would be to replace this with y, so I'm just going to write it right there, swap them, so this would now be x equals y squared minus 2. And if I were to go through and solve for y, I would first add 2, and then next I would take a square root. And this is where it gets a little tricky. When you take a square root, most of you, I hope, remember that when you take a square root, you're supposed to put a plus or minus symbol in front of it. So at this point, we would need to think in terms of, okay, I've got the square root of x plus 2 as what apparently I'm going to call the inverse function. I'll just write it as y here, and then over here I'll write it as the square root of x plus 2. But I need to decide out of the plus or minus which one is more appropriate based on how I just restricted the domain. Well, if we think in terms of what's a square root graph look like, well, the square root graph should look like, originally, something that starts at the origin and goes to the right, and it's kind of like half a parabola, but sideways. In this scenario, I have the plus 2 would technically move that left 2 places, so really this function would be something that I would want to be like that. Well, that should be the positive version of that square root, because the negative version would technically have been the upside down, because remember, a negative reflects it over the x-axis if it's out front. So based on how I restricted my domain originally and what the range actually turned into, notice the domain of that radical, -2, is what makes that equal 0 on the inside, and numbers that were greater than it would make sure that that stays positive. So my domain right here, that checks with what we just found, but the range I needed to make sure was the above 0 portion, which is why I don't want the negative version. So even though, yes, there was this plus or minus symbol, what I said for my restriction really was what I kind of based everything on. So had I originally gotten rid of the right side and actually had my domain be from negative infinity until 0, I would have then wanted to make sure that my range for the inverse was also the negative infinity until 0, so I would have wanted the upside down version or the negative version. So you have to be a little bit mindful of whenever you introduce something that has a plus or minus symbol, depending on how you restricted the domain, you need to make sure that you choose appropriately. Is it the right side up version of that graph, or is it the upside down or reflected version of that graph? For this one, I chose the right side, which was all positive numbers, so I kept the positive version. So anyway, hopefully this has helped in getting you to, be able to work through all of the practice problems. But as always, if you have questions, just reach out and let us know. I appreciate you taking the time watching the video, and we'll catch you guys next time.